Ordinary ordinary differential equations and vector calculus topic is solved problems on Bernoulli's equation. My name is Sai Charan. I am from Computer Science and Engineering Data Science Department. Introduction to Bernoulli's equation. Bernoulli's equation describes the conservation of energy fluid along a streamline. It applies to incompressible, inviscid, frictionless, and steady fluid flows. The equation balances pressure energy as per unit volume. It derived from Newton's second law, applied fluid motion. Its common applications include for measurement, aerodynamics, and mathematical form of Bernoulli's equation. P plus 0.5 stop P to P to the power 2 plus 2 G into H equal to constant, where P represents the static pressure with point in the fluid. 0.5 into to the power 2 is the dynamic pressure due to the fluid motion. Sigma into G into H is the hydrostatic pressure due to elevation. The sum remains constant along streamline under ideal conditions. Assumptions behind Bernoulli's equation. Fluid is incompressible. Density phi remains constant. Flow steady. Velocity at any point does not change with time. Flow is inviscid. No internal friction or viscosity effects. Flow occurs along a streamline. Equation applies between 2 points on the same streamline. The energy is added in derivation from energy conservation. Work done by pressure forces equals change in mechanical. Consider fluid element going between 2 points in energy per unit volume pressure, kinetic and potential components applying work and Monroe's expression. Problem 1. Horizontal pipe with carrying diameter. A horizontal pipe narrows from 0.2 meter to 0.1 meter diameter. Water flows at 2 meter per second in the wider section. Find velocity in the narrower section using continuity equation. We apply Bernoulli's equation to find pressure difference. Assume no elevation change in increasable flow. We can see solution problem 1. We can step by step explain here. Continuity A1 into V1 equal to A2 into V2. That implies V2 equal to A1 by A2 into V1. As per problem here given ratio, area ratio 0.2, this is A1 and 0 A1 is 0.2, A1 by A2, 0.2 by 0.1 whole to the power 2 equal to A2 4, V2 not given here, V2 equal to 4 into 2 equal to 8 meter per second. Bernoulli P1 plus 0.5 mega V1 will be equal to 2 P2 plus 0.5 omega V will be equal to H1 equal to H2. Rearrange this one. P1 minus P2 equal to 0.55 omega into 2 minus 1 over 2. Substitute this one. Omega equal to 1000 kilogram per meter cube. The delta P equal to 0.5 star into 64 minus 4 equal to 30,000. 30,000. This is the final answer. Venturi meter application. A Venturi meter measures fluid flow rate in pipe as considered through increased velocity and reduced pressure. It measures pressure difference between inlet and throat. Bernoulli's equation releases pressure drop at flow speed used in HVAC devices. Solution to flow rate calculation. Given D1 equal to 0.15, D2 equal to 0.05, delta H equal to 0.3. Mercury 5 Hg equal to, this is 13, 1600 kilogram per meter cube, water omega equal to. Problem 3. Tank or orifice. A tank filled with water, a small hole depth below. This is problem we can see Bernoulli P1 plus 0.3 omega V to the power 1 2 plus omega pH1 V2 plus 0.5 omega V to the power 2 plus PGH2. P1 equal to P2. P1 equal to 0 large tank H1 minus H2 equal to H simplify. Omega GH equal to 0.5 omega V to the power 2 V2 equal to square root gram to GH. This is Paul's law exits speed like free fall from hydrogen. Example H equal to 5 meter, V equal to square root 2 into 9.81 into 5 equal to 9.9 meter per second into 9. Problem 4. Lower airfoil consumption. Air flows faster over the curved upper surface and airfoil Bernoulli's equation explains pressure differences. Higher speed, lower pressure on top surface. Pressure difference creates slip force. Assumes inviscid, incompressible or attached. Solution to problem for lift estimation. Major velocities V top equal to 60 meter per second, V bottom equal to 50 meter per second. Assume sea level air, omega equal to 1.225 gram per meter cube. V bottom equal to 101.325 pounds. Apply Bernoulli. P top equal to P bottom plus 0.5 omega. P bottom whole to the power 2 minus V top whole to the power 2. Calculate now. We calculate P top conference 101.325 is 0.5 into 1.225 into 2500 minus 3600. That equal to 99,800. Pressure difference in your delta P equal to 1 comma 4 center points lift equal to delta P into star. This is 99,000 into this one. Next. A siphon transfers liquid over an elevated barrier using gravity for continuous long as outlet is below liquid surface. Bernoulli explains pressure and velocity at key points, maximum height limited by vapor pressure and captivation. Common drainage problem by applied Bernoulli between reservoir surface 1 highest point P1 equal to atmosphere, P1 equal to 0, H1 equal to 0.2. Common misconceptions and limitations. Bernoulli equation does not apply viscous to turbulent flows. It cannot be used across streamlines in rotational flow. Energy losses due to friction are ignored. Real systems need corrections. Compressibility matters, high speeds. Numerical example, static field. Major aircraft AFP using total static pressure. Total pressure P total equal to P static plus 0.5. Rearrange equal to square root into P total minus P static. Calibrated for standard air density at altitude. Used iovation. Problem solving step. Identify two points along a streamline for analysis. Apply continuity equation if cross-sectional areas are first. Write Bernoulli's equation with known as unknown quantities, substitute values, and solve algebraically for desired variable. Check assumptions, incompressible steady, indigit, new energy input. Applications. Fluid flow model support environment data analysis, Bernoulli based sensor generate time series, and elements understanding improves future engineering predictive systems. Topic Bernoulli equation. In this case, we have discussed 5 problems, Bernoulli's equation, and also formulas. So, thank you.